If we had to summarize the overarching themes of the topics of the last few videos, it might be a little bit tricky, but what we probably could say is they all touch on this idea of how a function changes. Now, that specific idea is one of the main ideas of a calculus course, but the way we're going to approach it is to sort of begin to dip our toe in the water. And we've done this a lot and explored this a little bit already. We've talked about how functions can change in a general sense, right? They could be increasing, decreasing, or constant. And with linear functions in particular, we got a bit more specific, right? We talked about slope and how an increasing function is one that has a positive slope, and a decreasing function is one that has a negative slope, and a constant function is one that has a zero slope. And then we took that a step further than that to say that if you had a really steep inclined line, one that was rising very rapidly, that could be quantified by a very large slope. And on the other hand, if we had a almost flat line, one that was climbing very, very slowly, that would be quantified by a really small slope. Now this is really great and really detailed and useful in the case of a linear function, right? In the case of a line. But how can we take that same sort of idea and apply it to something different? Perhaps something that looked like this. Now this can get a lot trickier, so a lot of the nuances we'll save for a discussion in calculus. But one thing we can do is look at this function in general and see an overall trend, right? In general, while there are some points where it might look like it's starting to decrease, it is trending upwards, right? It's overall increasing. You might even say, on average, it's increasing. And this is where our idea of an average rate of change can come in. We might not yet be able to compute the specific rate of change at any given point along this line, but what we can do is sense that overall general trend. And we can do that roughly by identifying a point where we're starting, identifying a point towards where we're ending, and drawing a line between them. And that line, just like all of the linear functions we've talked about previously, has a slope, has a rate of change. And we can utilize that line's rate of change to give us some sense of, on average, how much is this function changing? And that's what we'll explore in this video. So we'll let the point x1, f of x1, for our function f, and x2, f of x2, be two distinct points for our function. So be two distinct points on the graph of function f. And maybe we'll even draw a picture. Maybe this is our function, and here's x1 and f of x1, and maybe here's x2 and f of x2. And so these two dots represent our two distinct points along this arbitrary function f. We can define the average rate of change, so the average rate of change of our function f from the initial point x1 to the new point x2 by the expression f of x2 minus f of x1 divided by x2 minus x1. And now if you look at this closely and we think back to our previous videos, this really resembles the expression for slope. Right there we said m was equal to the rise over the run, or the change in y, right, y2 minus y1, over the change in x, x2 minus x1. And that's really all we have here, right? Yes, we're writing y2 and y1 in terms of function notation, right? We're saying f of x2 and f of x1, but as we've discussed previously, we can sort of use those interchangeably, especially when we're talking about graphing. And so we can say the average rate of change is defined by this formula, but just as accurately, we could say that the average rate of change is defined by the slope of the line between those 2 points. So in other words, the average rate of change, which I'll just abbreviate AvgRoC, right? The average rate of change equals the slope of the line between x1 and x2. And thus we have an expression that looks almost identical to the one for slope. Now, why might we care about this? What can we use this for? Well, let's consider a practical example. Let's say that you started training for a marathon, right? And you were going out there every day and running some number of miles. To make sure that you were on track, you decided to track how many miles you were running each day for a given week over the course of a 12-week training plan. And so we have a table here which lists the week on the top row and the miles ran per day in the bottom row. And we can get a sense just by looking that those are changing over time, right? In week 1, we had 1.5. By week 3, running 2 miles. By week 8, running 2.3 miles per day, and so on for the 12 weeks. One thing that we might want to track is, on average, how much are we adding on each week? And so let's say that we wanted to compute the average rate of change from week 3 to week 7. As we now know, our average rate of change is equal to f of x2 minus f of x1 divided by x2 minus x1, or the slope of the line between those 2 points. Now, of course, here we're working with a table, so we don't necessarily have a line we can look at on a graph, but we can still identify what our x values are and what our f of x values are. Right, in this case, our independent variable is going to be the week, and the dependent variable is going to be the miles ran per day. In other words, the miles ran is a function of what week we're on. And so here, our x values will be 3 and 7, and our f of x values will be 2 and 2.5. And so if we take those numbers from our table and plug them in, f of x2 is going to be 2.5 minus f of x1, which is going to be 2, divided by x2, which is 7, minus x1, which is 3, and then we can do the arithmetic to find that average rate of change across that 4-week period. And so we have 2.5 minus 2, which is equal to 0.5, and then we have 7 minus 3, which is equal to 4. Simplifying this a little bit, 0.5 we know is equal to 1/2 divided by 4, or in other words, 1 over 2 times 4, which is equal to 1 over 8. And so in other words, on average, we're adding 1/8 of a mile each week from week 3 to week 7. And so we can say, therefore, from week 3 to week 7, we're increasing our mileage by an average of 1/8 of a mile each week. And so 1/8 of a mile per week is our final answer. Now, as an additional note here, because we call this the average rate of change, it might be worthwhile to take a moment and check this with how we previously thought about what an average was. You may be familiar that for a set of numbers, the average would be the sum of all of those numbers divided by how many there are. So if we're talking about the averages of the changes from week to week, and we looked at how much this function was changing each week, so negative 0.2, positive 0.2, 0.25, and 0.25, and added each of those up and divided by the number that there are, so divided by 4, we would get negative 0.2 plus 0.2 plus 0.25 plus 0.25, all divided by 4 because we have 4 data points here. And this sum up top, negative 0.2 and 0.2 would cancel out, and then we've got 0.25 plus 0.25, which equals 0.5 divided by 4, or exactly the same thing that we found up here, which is equal to 1/8. And so either way that we slice this, either thinking of this as the slope of the line between those 2 points and computing it with the average rate of change formula that we found, or treating it like an average as we previously have thought and used that word, we're going to get to the same thing, at least in the context of a data table like this one. If we did have a continuous function though, for example, like f of x equal to x cubed minus x squared minus x plus 1, then utilizing the average rate of change formula, in other words, the slope of the line between the 2 points, is going to definitely be the easiest way forwards. And so let's see if we can apply that here as well. If we want to compute the average rate of change of this function from -1 to +2, then we can utilize our average rate of change formula. We know that the average rate of change is equal to f of x2 minus f of x1 divided by x2 minus x1. And so all we'll have to do here is evaluate f of x2 and f of x1. And so we'll have f of x2 is now f of 2, and f of x1 is f of -1. x2 is 2, and -1 is -1, and so we have 2 minus -1. f of 2 we know is going to be defined by this expression here, where we substitute 2 in for x, since that's our input. We can plug in and get 2 cubed minus 2 squared minus 2 plus 1, and then subtract f of -1, which is where we plug -1 into this expression. It will be important, as always here, to make sure we remember our parentheses, because we are subtracting the quantity f of -1, the output that we get from that function. And so we want to make sure we keep that quantity together by using parentheses. But as long as we remember that, we should have minus -1 cubed minus -1 squared minus -1 plus 1, close parentheses. And all of this will still have to be divided by 2 minus -1. Now, starting to simplify and do the arithmetic, 2 cubed is going to give us 8, minus 2 squared. 2 squared is going to give us 4, so minus 4 minus 2 plus 1. And then minus -1 cubed. If we multiply a negative by itself 3 times, that's still a negative, so this will be minus 1. If we multiply a -1 by itself twice, if we square it, that's going to become positive, and so this will be a minus +1, or minus 1. And then minus -1, 2 negatives will make a positive, and so we'll have plus 1. And then carrying our plus 1 down from there as well, another plus 1. And once again, 2 minus -1 on the bottom would be the same as 2 plus 1, because we're subtracting a negative. This might look like a lot of arithmetic to do, but what we can notice is this section here has 2 minus 1s and 2 plus 1s, and so those will cancel each other out, leaving us with 0. And then we can do 8 minus 4, which is 4, minus 2, 4 minus 2 gives us 2, and then plus 1 gives us 3. And so we have 3 minus 0 in the numerator, divided by 3, because 2 plus 1 equals 3, in the denominator, giving us 3 over 3, or 1, as our final slope. In other words, on average, our function is changing at a rate of 1. The slope of the line between the points -1 and 2 is positive 1. And if we graph this line, we can observe this as well. Right, starting from this point, we know that a slope of 1 would mean to go over 1 and up 1 to reach our next point, right? The rise and the run are both 1. And so if we go over 1 and up 1, that brings us here, which is also on the line. If we continue going over 1, up 1, that brings us here. Once again, going over 1, up 1, that brings us here. And so we can see that all of those points with a slope of 1 lie along this line. And so that does indeed confirm our answer. Hopefully you found this interesting so far. Like I said, this is kind of just our first step into ideas that we'll explore in a lot more depth in a calculus class. Namely, how can we discuss rate of change of functions that are varying quite a bit rather than lines that tend to change at a steady rate. This gives us some sense of that with at least our ability to describe how they change on average, if not quite yet very specific at specific points. And so hopefully this is helpful, but also hopefully it gives you something to look forward to as you move into a calculus class in the future. But either way, as always, let me know if you do have any questions or if there's anything that I can do to help, and I hope you have a great rest of your day.